Hey students, let's go ahead and do part 2 of the mechanisms, simple machines, and in this case we're going to talk about the inclined plane, the wedge, and the screw. Alright, so let me switch it over to, um, so um, of the 6 simple machines we've already talked, and I talked a really long time, and I'm sorry about that, but let's talk about the inclined plane, the wedge, and the screw in this case. So this won't be nearly as long, but um, we will continue to work through it. All right, so again, review on mechanical advantage, right? Mechanical advantage is the ratio of the magnitude of the resistance and the effort forces, or the distance traveled by the effort and the resistance force, okay? And we calculate these so we can manipulate our speed, manipulate the distance that we travel, manipulate the force that we need to use, and really change the function. And remember, all of these simple machines are so we can do work. Okay, so in this case, we're using an inclined plane to do the work of lifting this block a certain distance. So let's say 1 foot. So we have a 1 pound block that we're lifting 1 foot. Or we can slide it up the inclined plane and use less force, all right? Because if I lift a 1 pound block 1 foot in the air, I'm going to be exerting 1 pound of force to have it lift into the air, right? Or I can exert the force, much less, like maybe a tenth of a pound, all right, to push it up that ramp, and it will do that work. The same amount of work over a longer distance, but I can use less force. Okay, so that's the part where we talk about trade-offs. In this case, we're trading off using 4 times less force by exerting that force over a longer distance. Okay, we still do the same amount of work. It's still at the end of the day the same height above the ground, all right, but we exert that force over that inclined plane, and that allows us to get a mechanical advantage of 4 to 1. So it's 4 times less magnitude in the resistance force. Okay, but there's a trade-off in engineering. We don't get anything for free. So if we exert 4 times less force to push it up the ramp, our effort distance has to be 4 times longer, because that's the trade-off. Nothing is ever free in engineering. Okay. And again, just as a reminder, 1 is the magic number here. All right, if the mechanical advantage is bigger than 1, then we're going to use less force and more distance. And if it's less than 1, we're going to be using less force and more force and less distance. So if the mechanical advantage is under 1, and remember that it never, ever, ever is equal to 0 or a negative number. So it can never be less than or equal to 0. All right. And again, this is just a review. You have this in your notes. The IMA equals the distance effort over distance. And I'm going to write this on my paper because I have a new paper. So distance effort over distance resistance. Okay, so that's ideal. That's in a perfect world, does not account for friction. And then we have our actual mechanical advantage, and that is in the real world because it's something that we have measured. So we have the force, resistance force, and the effort force, or force effort. Okay, so AMA equals FR over FE, force resistance, or resistance force, and force effort, or effort force. Okay. So we're talking about 3 different items today. The first one of those is the inclined plane. Okay, so inclined plane is just a flat surface set at an angle. It does not have any moving parts, and it's able to lift objects by pushing or pulling the load. And we see this all over the place in wheelchair ramps, in roller coasters. And then if we get really, really technical, we can see a screw. A screw is just an inclined plane wrapped helically around an axis. Okay, so when we do the IMA, All right, again, same formula as before, what you've written down in your engineering notebooks. Distance of your effort divided by distance of your resistance. Okay, so in this case, it's the length of the slope, all right, divided by the height. Okay, so we see here distance traveled by the effort. All right, that is the length of the slope. All right, that's the travel distance that we've done. By the height, distance of the resistance is how high I moved it. All right, and that makes sense, right? If I have a short slope and a big height, all right, it's going to take me more force than to push it than it is then, and so I'll have less mechanical advantage than if I have a really long slope, a really big number here, with a small height. All right, so I'll be dividing it into with a smaller number, which gives me a larger number. So I have more mechanical advantage the longer my slope is in relation to my height. Okay. So if we look at what's the IMA of the inclined plane above, length of the slope, 15. Divided by height, which is 4, so 15 divided by 4, whatever that comes out in your calculator, 3.75. So if we round that up, 3.8 to 1. All right. So we do have a positive mechanical advantage, so it takes us less effort to roll this cart up the plane than if we just lifted it up on our own. All right, so that was ideal mechanical advantage. What is the actual mechanical advantage? So that is the forces. All right, force of the resistance over the force of the effort. So resistance force divided by effort force. This is something we would have to measure as I'm pushing it up. My force meter is reading 20. Remember, the effort is in the direction, is parallel. All right, so I'm exerting 20 pounds of force to push it up. Right, and this cart currently weighs 50 pounds, all right, because gravity is pulling it down at 50 pounds. So if I put that into my equation, right, my AMA is 50 pounds resistance force, right, which in this case is gravity, 50 divided by 20. All right, the pounds cancel, so it's unitless. All right, so that gives me an actual mechanical advantage of 2.5 to 1. Okay, if we go, what's the efficiency of the inclined plane, which is AMA divided by IMA, and you should have written that down in the previous lecture. All right, times 100, which is just moving the decimal place 2 places. We plug that in. AMA was 2.5 over 3.75 from the previous slide, and we work that out as our percent efficiency, and we get 67%. Okay, so efficient, but not extremely efficient. The second thing we want to talk about is the wedge. Okay, this is simply an inclined plane that is moving. Okay, it tapers to a thin edge just like an inclined plane, and we use it for splitting wood. We will put wedges into, we call them shims, into window frames to hold them in place, to wedge them in tightly. And that's the last part, tightening by being driven into something. All right, so we can shim a window to lock it into place where it's vertical and horizontal to the ground of the walls. In this case, IMA is still DE over DER. Do you see how this equation just keeps getting used? All right, there's a little wrinkle in that it looks different, but again, with the wedge, all right, it's the length perpendicular. Okay, so in this case, right, we're not measuring along the length. Okay, this is the wrinkle because we have two planes. All right, two sides of this wedge. Right, we're measuring the perpendicular, so 90 degrees to the height. So height is how wide or tall, however it works in your brain. We turn it on the side, it makes sense for height, right? In this case, it makes, in my brain, it makes sense for width, whatever works for you, all right? But then the perpendicular distance, that's the 90-degree distance, all right? So in this case, what's the What's the IMA of this wedge, right? We have the length, the perpendicular length of 10 divided by 3, which is the height, and that gives us 3.33 repeating. Okay, so 3.3 to 1. Okay, so we're getting a mechanical advantage of about 3.3. All right, AMA, same thing, resistance force over effort force. All right, so what's the AMA of this wedge? And we have measured this. Okay, so again, AMA is real world. All right, I am pushing down with 250 pounds of force, and I'm getting 700 pounds of force on one side and 700 pounds of force on the other side. Because again, the wedge is really kind of like two inclined planes together. That's why it's a little bit different. All right, in this case, we are taking the 700 pounds here, dividing by the 250 pounds of the other, okay, because we're really just we're going to use half of it, and that gives us a actual mechanical advantage of 2.8 to 1. Okay. And then what is the efficiency of the wedge? And so you're only going to use half. You're not going to use 700 on both. You're only going to use the half. And a lot of times you'll just see it just as the one. You won't see the two there. But no, if it's a two-sided wedge like this, it is exerting to either side. Okay. And then so AMA over IMA, you get 2.8, which we just calculated, over what we calculated on the previous page, 3.33 repeating. Multiply that times 100 to move the decimal place, and we get an efficiency of 84%. Okay, as we talked about this before, as I mentioned before, a screw is really two things. It is an inclined plane that's wrapped around a cylinder. That's what I mean by helically around an axis. It's a coil. All right, so it forms a path and a pitch. Okay, the path is if you put your finger on one of the threads and followed it around, you're following on the top of the inclined plane, which is the path. And then the pitch is the distance from one thread to another. Okay, we use screw threads a lot. It's super handy in engineering to change rotary motion into linear motion. So I have something that's turning, right, and that drives something in a straight line. We see that in lathes quite a bit, right, or a bolt, right. As I tighten it down, as I turn, as I rotate, all right, it pulls two things together. Okay. It has a super large mechanical advantage, which means I can get, with a bolt, I can tighten it down and get some really strong forces. But because nothing in life is ever free, there's a lot of friction force. And you can feel that, right? As you tighten it down, that friction gets greater and greater and greater, and you have to exert more and more torque to get it to turn. All right, so in our screws, okay, if you're using a wrench or your arm, the effort distance is going to be the length of your wrench. All right, the place where you are grabbing to turn it. It's not the head. All right, this makes it look like it's the head of the wrench, or the head of the bolt. But if I put a wrench on here and it goes all the way out through here, wherever that wrench ends when I'm grabbing it, all right, that's going to be your effort distance. All right, that's the work that you're putting into it. Okay, pitch is the distance between threads that's traveled by one rotation of the screw. And I like to think of it like from one peak to another peak, or one valley to another valley. Okay, and you should have learned this in IED, right? But when we look at a thread callout on a drawing, first number is the diameter of the thread. Okay, so that's the nominal diameter of the thread. And then the second number is how many threads per inch. All right, so if I've got 13 threads per inch, then the pitch is going to be 1 divided by 13, 1/13 of an inch. So just in your calculator, do 1 divided by 13. And that's going to be the distance between from here to here. Because we know we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we know from here to here is 13 threads. That's 1 inch. All right, so threads per inch. And then the last one is coarse or fine, or in some cases ultrafine. All right, but we have a C for coarse. Don't get too worked up on the N. I think it stands for national because this is the Unified National Code, UNC threads, but just means coarse. If you saw NF, that's a fine thread, and it basically means how well the threads are made. Right? How pointy is the point? How round is the bottom? All right. So if I turn it 1 full rotation, how far is this screw going to go? How far will it go in or out? This bolt. It's not a screw, it's a bolt. All right, 1/13 of an inch. All right, same equations as before. Effort distance divided by resistance difference. All right, so 1 rotation of the effort arm equals your circumference. All right, so this equation is a little bit different. You might want to write this down, right? So IMA is going to be circumference divided by your pitch. All right, so your effort distance is going to be 1 rotation of the wrench, and the resistance distance is going to be how far it moves down. All right. So if you think about it, we have great mechanical advantage because we're taking a wide swing of the wrench, all right, and only moving just a tiny bit, like 1/13 of an inch. All right. So your equation is going to be IMA equals 2 pi r, okay, circumference, over pitch. All right. So 2 pi r over p. So you might want to write that down in your engineering notebook. Just so you know, for a screw, all right, then it's going to be 2 pi r over p, the pitch, and I would write out what pitch is, so you know that. But in the case of this up here, so this is a 1/4 inch, okay, diameter, all right, so we've got to be certain to change it into a radius, all right, so we have to do half of that, so 1/8, all right, and then we multiply it by pi. All right, so 2 pi r, so 2 times pi times the radius, and then divide that by the pitch. In the case this pitch is 20 threads per inch, or 1/20. 1 divided by 20 is the pitch. All right, so in this case, so 1 divided by 20, and then that leaves us, when we calculate it out, skipped a step, sorry. So what is the IMA of the screw above the effort applied by an 8-inch long wrench? All right, so we have 2 pi times the 8-inch wrench, all right, divided by the pitch, so there's the circumference, divided by the pitch, which is 1 over 20, and you work all that out, and you get 1,005. So mechanical advantage of over 1,000. All right, super important. Now, many of you are probably going, Mr. D, I don't know where that 8-inch is coming from. Okay, this is probably a better picture. Okay, I have a wrench on there, right, and that wrench from the center of this bolt head to the end of the wrench where I'm grabbing it to give it a turn. All right, that's where the 8 inches is coming from in that previous problem. So if we look at AMA, the resistance force over the effort force, again, same equation, all right, same formula. All right, so I'm turning, right, with 35 pounds of force on my 8-inch wrench, and I'm getting 1,200 pounds exerted downwards, pulling the two pieces together. So 1,200 divided by 35, all right, and then if I multiply that, and then that gives me that gives me an AMA, an actual mechanical advantage of about 34 to 1. Okay, lots of friction. So look at the difference, right? The ideal mechanical advantage is 1,000, right? And we now have a actual mechanical advantage of 34. Where did all of that? What? Wait, it's 1,001 ideally, but we're getting 34. Why is the number so different? It's because there's a lot of friction. All the way around that path as you drive this down, right, wherever the thread is meeting, it's grinding against one another to pull itself together, all right, and all that grinding against one another as you tighten it down is creating more and more friction, okay, and so you lose mechanical advantage because you are losing work in the form of heat and sound when it squeaks when you tighten it together, and so that's all lost work. It's all friction loss. Okay, and then we can figure out the efficiency. AMA over IMA times 100. Just move decimal place twice. And you get an efficiency of 3.4%. So you see it's not very efficient, right? But we get some really good mechanical advantage, and we use it all the time to pull things together. It's just like, if you've ever turned a screw or tightened a bolt, like you feel like you're turning forever and ever and ever and ever. You have to put a lot of work into it to get that so it's not very efficient, right? That's why we have screw guns. Okay, and we talked about this. Why is efficiency so low? It's because the friction losses are incredibly high. Okay, and then I think this is the probably the last slide here. Compound machines. I think yes, it is the last slide. Compound machines. They're just simple machines working together. All right. In that case, just like we talked about before, you're going to multiply them together. So figure out the mechanical advantage of the first thing, figure out the mechanical advantage of the second thing, figure out the mechanical advantage of the third thing, and then just multiply them together, and then that's the total compound machine's mechanical advantage. And all they mean by compound machine is just a series of simple machines working together. All right. So in the case of the bicycle, we have several pulleys working together. We have, a mechanical advantage for the rear tire and a mechanical advantage that's being applied by the sprocket here. Mechanical advantage applied by this lever that is all right, so we got a couple pulleys. We have a lever here that we push down on. And then, another wheel and pulley this has an axle that turns as you push down. So it's all, and it doesn't really provide you any mechanical advantage, but it's all combined you multiply together. All right, so we'll do some more practice on this, and so we'll use all this in combination, and as you practice it, it will start to make more sense to you. Okay, all right, thanks guys.